I'm the Sarah, this is the Ian, but we do need to talk about everybody else who contributed. So 2 of which are right in front of us. So Ryan, Madeline, up, wave. Talk to Ryan about the maritime stuff, talk to Madeline about the autonomous vehicles. And yeah, a lot of people, you'll see a huge long list of people. So going to talk about autonomous resilient cyber defense. And ARCD is a UK program. It's about 60-ish, maybe more millions over 4 years. But it's, last time I counted, it was well over 100 different projects across dozens of organizations across the UK. And we're seriously proud of that. But the idea is that defense has a problem. And the problem it has is there aren't enough cyber responders. And there sure as hell aren't enough cyber responders in the places that you need to do all the cyber responses. So especially at the tactical edge, so places where you're starting to put autonomous vehicles into, again, see under leader-follower stuff. But you tend to have operators there, they're not necessarily cyber operators, and they tend to be kind of busy doing other stuff. So you need some form of first aid, you need some form of response repair going on. The second problem we have is that we're working on automation. Sure as hell the bad guys are working on automation. So we're expecting to see the 3 Vs again. We're expecting to see attacks coming in at speeds, volumes, varieties that would overwhelm a human team. So we need to respond at machine speed to machine speed attack. And we looked at things like SOAR, but we have some very specific issues. One of them is that our context changes. Operating as normal, suddenly you're in a hot zone, the way that you operate changes. And we have like kinetic issues with changing our networks in other ways. And also, we have missions and changes in missions. So we have to think very much about not how do we just protect the system, but how do we protect the mission that the system is based on. So I'm going to talk about metrics in a little while. So 100+ projects, 4 years, what do we get up to? So here are the people. So DSTL, that's where I work. We lead the overalls. We have a small team at DSTL, but we also have a lot of work coming from Fraser Nash. Fraser Nash manages the concepts, so a lot of the research projects. So Ian leads part of that. We have Kinetic, who are leading the test and evaluation on this. So much more the engineering stuff, much more the what is important, how do you build environments to test all this in. And we have Alan Turing, who spoke yesterday, who are doing really low levels. So if you know what TRLs, they're doing TRL 01, Fraser Nash are doing up to about 5, and then we're looking up to how do we actually make this real. Partnerships, we obviously, Ministry of Defence, other bits of the UK government, but we also talk to DARPA. DARPA has an equivalent project called Castle. We work with Five Eyes, so Australia, New Zealand, America, Canada, ourselves, on things like the Cage Challenge, which go do the Cage Challenge if you want to understand this. And then, yeah, suppliers, lots and lots of suppliers. And what we're building is these little unicorns. So when we started, it was relatively rare to find machine learning InfoSec people. Had to go hunt for them. And these suppliers have built their own teams. They've taken cyber people and data people, they've cross-trained, they've worked together. That's the unicorns. Deeply proud of those, deeply proud of the startups we built around this. We're responsible for several, some of which weren't exactly expecting to start companies, but what the hell. But we also have this third thing of military systems. You've got to understand all 3. So unicorns, and then we have the real treasures, the ones that get all 3. But most of these are teams. So that's who it is. This is what we're doing. So if you kind of look at what we're doing, cyber threat detection, you need to do threat detection to do this. That's a different program. So we're actually, if you're looking at NIST, we're doing respond recover. A little bit some other parts, but mostly respond and recover. So this thing has happened, what do we do to make it less terrible? How do we recover our systems? In a really difficult, interesting environment. So for our side, we need to work out how to integrate these ideas of autonomous, fast cyber defense into real-world context, real-world systems. So you're going to be seeing a lot of that with Ian in a minute. But we also need to think about, we're talking about bots, and what is appropriate input to them. And I don't mean take the PCAPs and shovel them around a bit, but you're thinking about things like intent and prediction and who is this so we can understand what they're likely to do next in our systems. So situation awareness. The part that we're talking about today is only a small part of the whole program, and we're talking about a small part of that part, and that's the machine speed response and recovery part. So this is the algorithms, the agents, the systems that we need to understand this in. There's fundamental research. We're doing everything from make this go faster with quantum machine learning through to things like explainable AI. And then there's governance assurance. So these things, I mean, you're putting a new system onto a system that you're trying to protect for vulnerabilities. You've just added another threat surface. So we need to understand, is this secure in itself? Is it safe? Because a lot of these are safety critical systems. Is it ethical? And ethics is kind of fun. I'll talk about that in a minute. But you can think of ethics as part of risk. So you're thinking about what is the risk I'm adding to this versus what is the risk we're reducing. So big buckets, that little part of that red one is what we're talking about today, because we could honestly talk for days on this stuff. So what's this based on? So autonomous cyber defense systems, ACD. Already around. There's been some great work coming out of NATO's IST-152 and the follow-on AICA. There's been good work in lots of different places. And what this basically is training up cyber defense agents. So an agent is a piece of code, a subsystem that's situated in an environment, it senses its environment, it acts in its environment. In this case, those actions are basically TTPs or variant solve. So we want these to respond and recover in real time. These are blue agents. You'll also see in these systems red agents and green agents. So when we run simulation, when we train these, green agents are ways to emulate user activity, so normal users. Red agents are the attackers. We need to emulate those too. If you're training both the red and the blue, then you've got an autonomous cyber operation system. So those two terms you can look up. So observation, talked about, can you detect an attack, convert those into infosec feeds, enrich it, acting, basically TTPs. And this can be rule-based, this can be probabilistic. If you squint at a lot of existing commercial systems, they can look like ACD. But we go one step further, we train them, we make them adaptable, we make them slightly more interesting. But the actions, some systems, the bots, the machines can act themselves. Other systems, you have to persuade a human. So there's a whole bunch of layers on that, on things like explainability. So training. I data scientists, learning algorithms. So reinforcement learning. Has an agent, sat in an environment, takes actions, those change the state of a world, which also changes from other actions. You get a reward signal. Basically think of games. They've been used a lot in automating game agents. And you go around the loop again. You act, reward. Your reward in this case is have I stopped this attack or contained this attack or contain parts of this system? Is it still operating well? So again, complex. Talk about it in a second. So algorithms, RL, variants of RL, multi-agent RL, you see was talking about this. LLMs are being useful for things like producing example systems, producing that green traffic. And there's a bunch of other algorithms we've tried, generative algorithms, graph neural networks, and we're getting a lot of good stuff out of combining algorithms coming through. But you've got issues with that. Scale. We're talking big systems. So reinforcement learning, the size of vectors is enormous, so it's a lot of work on how do we either deal with or reduce that scale down. You don't get to see all of it, partial visibility. Rewards, it's cyber. So you're either going to get attacks coming in all at once in one big burst, or you've got low and slows, you've got normal traffic, you've got to deal with that. And one of the things that happens is you need a lot of data, typically. Again, something to work on. But data sets available for MLSec generally are detection data sets and not necessarily action data sets. So it's hard to get those. So again, stuff we work on. Generalizability. World changes. Attacks change. Attackers change. You've got to be able to deal with that. And explain to the humans, explain to the users, but also explain to the safety people, people who are checking this. So a couple of research questions. What is good? So for AI, for a long time, good was, hey, I've got a system, I'm training it, I want my F1 score. Has it met the F1 score? Is it doing well? Then we discovered people can attack these systems, so how robust is this? And then we discovered ethics. So, what is the risk in this? We've got a lot more. We've got to think about not just robustness and trust, but we've also got to think about how does this affect the mission? How does this fit the containing system? All the way back down to those simple parameters. And we have a bunch of simulators. So the top line, so simulators, because if you train in the real world, you take bloody ever. So you have abstract representations, you train in that, then move it over, sim to real. 3 systems there you can pull off GitHub. Emulators, cyber ranges, so real hardware operating within, or real software operating within those simulators, and then to the real world. So sim to real, moving between those, you've got issues like most simulators are doing tens of nodes in networks, where those nodes are, routers, switches, PCs, whatever. We're looking at hundreds and thousands, big systems. We're looking at, when we move to the real world, it's more uncertain. You're just going to get uncertainty off things like intrusion detection systems. You've got to deal with that. Real-world actions don't necessarily always happen, especially if you're persuading humans. And just the bottom line of you're doing this in the real world, you've got to deal with integration too. So I've just given you the background. I'm going to hand over to Ian to talk about the things we actually did.
Okay. Yep, great to be here. So I will just caveat, we're not able, because of the breadth of the programs we're looking at here, I'm only able to go into a limited amount of technical detail. There is a technical paper that will be uploaded to our site in support of this talk that will give you a lot more technical detail. But let's go. So just as a bit of an overview, we're going to start looking at our initial proof of concept. We'll then move on to trying to expand that and trying to make it able to generalize. How can RL be used to deploy onto unseen networks or defend against a wide range of attackers? We'll then move into how do we actually bring this into the real world. So the Cyber First Aid project aims to perform some simple tasks, simple autonomous tasks, in order to buy time for a human expert. And then we move into our larger projects, which are looking at full deployment to military OT. So in terms of our initial proof of concept, we set up quite a simple simulated environment where you've got a denial of service attack being launched from the botnet on the left-hand side here, aiming to overwhelm server 1 in grey on the right-hand side. Through quite a small amount of training, our RL agent was able to quickly learn appropriate behaviors here, which was to set up firewall rules to block traffic from the infected nodes, which was a really great response. Even at that early stage, it gives a really good insight into how RL, the benefits that RL can bring to this problem. The RL agent even went as far as outscoring a rules-based agent that we'd worked up with our human cyber experts. However, this is one of the pitfalls of any machine learning. We found that this agent was actually gaming the scenario and repeatedly making small actions and gaining extra small rewards that weren't necessarily needed in reality. So again, it's just evidence of how you need to, the assurance that's needed around these types of systems. Another interesting insight we gained from this project was that it was able to adapt to an unintentional misconfiguration of our simulated network. So a couple of the firewall rules are set up incorrectly. The human-based, rules-based agent wasn't expecting to see that, so it wasn't able to adapt automatically. The RL agent learned that through its training and was instantly able to overcome that and correct those rules. We also found when we had to make adaptations to the environments, the RL agent could quickly learn how to overcome those, just retrain and adapt to those changes, whereas the rules-based agent would need full revalidation to make sure it could operate in that scenario. However, whilst that all sounds lovely, this agent's completely overfitted to this scenario. It will be absolutely useless if you deploy it to any other network or if you launched any other attack on this specific network. So hence, as I said before, there's a big need for more generalized approaches that are a lot more robust than what we've got here. The first of the projects we launched into this area was aimed at looking at different network topologies. The problem we face here is the level of effort required to stand up these network configurations is quite high, especially the volumes that we need for a machine learning agent to train. The way we've overcome that on this project is we've embraced the progression in generative AI here, where we were able to develop a prompt into GPT-4, which was able to autonomously build us network configurations and provide variations on what typical tactical networks in a military environment might look like. So this is a huge gain for us, because this could have potentially been weeks, months of human effort trying to build these, and instead we're able to do this in a matter of weeks. The approach we've used for this specifically to address the generalizability, so now we have this bank of environments at network laydowns that we can use. The machine learning approach that we've used here is deep MARL combined with graph neural networks. So graph neural networks are inherently suited to the network topologies based on their graph structure. Through the training and evaluation process, we were able to show, as you can see on the figure on the right-hand side here, hopefully anyway, at least the size, that as you increase the number of training network configurations that are seen during training, the agent is able to perform better when it's deployed to networks that it hasn't seen before. We're now moving this piece of work out of simulation and into emulation. So we're now running it in a real AWS environment using real red tooling such as Cobalt Strike and Metasploit, and real blue tooling such as Elastic Defend. And this project is now going to move into a period of co-evolution learning, where the red and blue agents are going to learn together to improve both policies. We're hoping to get this to a point where we're going to be launching our first full-on red team exercise against an autonomous cyber defense agent early next year, which is a massive milestone for us and is going to be really important in gaining assurance for the performance of these systems. So another problem I mentioned about generalizability is different attackers. So again, handcrafting large volumes of attack trajectories to various different networks is a huge amount of effort. So what we've done here is we've been working with the biggest telecoms provider in the UK, BT, to create RL-based red agents, which we'll be using to train our blue agents. What they've done, as you can see on the diagrams on the right-hand side, they've developed reward schemes that bring in more complex behaviors such as stealth, effort, and persistence, which will bring new aspects to the red agents that we're training against. The table in the bottom right starts showing you how, from an untrained agent in the zero row, from the zero training episodes row, which was making lots of invalid actions in the network and was actually unable to reach its target, as the level of training increased, you can see that the number of invalid actions drops off very quickly, but we're still, midway through the training, we're still making some invalid actions, but also some duplicate actions, but we were able to reach the target. Further training, again, removed all the invalid actions here, and then we were able to reach the target with almost no duplication. And I'm sure with more training, this could have achieved perfect performance. We're moving this project again to look at co-evolution to train blue agents. And there's huge opportunities here, clearly, with working with a large telecoms provider. So an interesting thing that SJ mentioned earlier. So now we're introducing this fantastic new AI capability into our systems. However, unfortunately, we're now introducing a new attack vector as well, especially with future AI threats where we don't really understand what future TTPs might look like. This is a whole new area which frameworks such as MITRE, Atlas start looking into. There's also the challenge where the AI agents are going to be difficult to upgrade once they're deployed. So again, we need a robust solution that's able to handle different types of attacks. For this project, working with BAE Systems in the UK, we're again using adversarial learning, but we've developed a novel technology called multiple response oracles. What this aims to overcome is that sometimes in machine learning, you can experience something called catastrophic forgetting, where you may forget the attackers that you learnt in your early training, and your final policy may then be vulnerable to just experiencing those attacks because the various iterations on the policy has overwritten the defenses against those. As I mentioned, this approach is also aiming to improve ability to defend against novel attacks, but also risks of underestimating the adversary. So that's talking about where potentially our training isn't actually as sophisticated as the adversaries we might like to see. So the way the multiple response oracles overcomes this is it keeps a history of the different iterations of blue policy that it had. So it's always comprehending and remembering different policies it had. And the way it uses these is it uses game theory to sample from those policies to be able to use different levels of the policies, a mix where it's able to offer that balanced cyber defense solution. When deploying this, we're still quite early in this research. We're only for anyone familiar with it, we're only using the Cage 2 challenge, which only has 2 attackers in it. But we've adapted that to fight against a genetic algorithm-based attacker. And we got this to a point where the red agent could not win the game because of the robustness of the blue agent. We're now extending this work to far more complex scenarios. So Cage 4 was released earlier this summer. This is a multi-agent problem. This is a huge step change in complexity from Cage 2. And we're really hopeful that this will show promising results. So I've talked a bit about the generalizability problem. The other big problem we face is deploying to real systems. I mentioned the Cyber First Aid project. This is looking at hardware operating at the edge, where typically we'll have very little cyber expertise. So you can imagine, for example, a drone operator in the field. They just want their system to keep running. Their specialism is in operating that system, not in cybersecurity. The way we've approached that is this Cyber First Aid project aims to make simple actions purely to limit the spread of an attack. So it's not aiming to do full recovery and response and recovery, sorry. It's just aiming to contain the cyber attacks at source and then buy time for a human expert to come in and do the full recovery. Again, we train this in a simulator. We've trained this agent in a simulator, and we deployed it to a ROSBot. During testing of this, we were able to demonstrate our first end-to-end demonstration of ACD on a real system. So this is where the ROSBot was attacked with the real RDP overload denial of service attack, and it was able to recover in less than 1 second. So it's a really tantalizing insight into what the benefits this could provide in the future. Obviously, a ROSBot's very simple compared to a real military system, so we're now moving this to a full military drone concept demonstrator, where we're aiming to deploy to that system and train with it. And we've got field trials for that planned later this year. So OT has been mentioned a lot in this conference, right? So military OT has hugely specific applications. We're looking at future technologies. So in this case, we were looking at a semi-autonomous logistics vehicle. So if you imagine a manned lead vehicle followed by a chain, it's called platooning, a chain of autonomous vehicles following the breadcrumbs behind it. Again, you've got a task-saturated operator here with limited expertise. Their main job, they just want to get to their destination. They want to keep on the road. They're not going to have a huge level of cyber expertise, and they're definitely not going to be able to respond to an incident whilst they're running potentially in a wartime scenario. So the way we've addressed this project is that we've built another simulator which reflects real vehicle architectures. So There's something called the Generic Vehicle Architecture Standard, which is used in the military. This is based on a DDS bus. And what we've done is we've developed a multi-agent RL system using deep queue networks, where we've got approximately 30 agents that are deployed throughout the system, and they match the vehicle architecture, which is going to help us with future integration. Again, we're looking at a unique OT action space here, where we're not considering corporate IT systems. We're looking at power systems, fire alarms, navigation systems, very specific to the use case. This project, its key results has shown that the reinforcement learning can defend against simulated false alarms that might be used to potentially delay the vehicles, manipulated GPS messaging, which might be aiming to divert the vehicles into a dangerous area. And this is via interfering with DDS messaging rather than your typical GPS spoofing over RF. And there's also, and the other attacks we've considered is a denial of service on the vehicle-to-vehicle communications link. The approach we're using, which is offline RL, has had a lot of challenges in terms of scalability. However, what we believe is that because you're effectively generating a huge training data set, this makes it more supportable through life, because you can target areas to improve training rather than have to do a full retraining run if there are any changes to the system. Through this process, we're also developing really interesting insights into future ML-SecOps procedures and workflows that just don't exist at the moment. There's also opportunities to deploy this to a digital twin in the next year or two. As we scale up the OT, we've moved to a maritime system, an integrated platform management system. So this is effectively the brain of a warship. This is an industrial control system which is using sensor data, human inputs, etc., to control the plant and machinery on board and keep the platform operational. Again, whilst there are cyber operators on board the ship, these guys are typically very overloaded, and also due to the physical limitations of the fact that a warship's massive, the responses are naturally going to be slower. In this project, we've also done a lot of work digging into the impacts of uncertain data, so false positives, for example. This is an imperfect data flow that we're going to have to deal with in real life. So again, there's a common theme here. We've had to build an IPMS simulator, which tries to model the component interactions. And here we've modeled specifically a chilled water plant on board a ship, and also the power and propulsion systems. We've also looked at different levels of difficulty in the environment, where we've looked at the sensitivities on the different parameters, such as the false positives rate, and also the probabilities of an action actually succeeding. Here again, we've deployed multi-agent PPO, so PPO is quite a common RL algorithm, considered state-of-the-art. We're also using explainable AI, which we don't go into in much detail here, but it's a huge challenge for us in terms of ever getting user acceptance of AI technologies. At the minute, we're using it to support diagnostics, but there's a natural progression here for it to provide some context for the user as to why on earth the agents made certain decisions. This project is really exciting, where we're moving it now to a real proxy system. So this is a classified test rig, which is using real PLCs, real HMIs, real software which is highly representative of an operational warship platform. The diagram on the right-hand side is really looking to try and explain this transfer learning approach that we're using throughout a number of our projects. So at the top there, we build our simulator using standard ML libraries and technologies. We then train our ACD agents within that environment, here using RLlib. We then had to build a middleware layer. So what this does is the simulator is running in an abstract world. With this middleware layer acts to translate between the real world and the simulated world. So what the agent will receive abstract observations, and then it will make these abstract actions on the network. So it might say, oh, can I isolate node X What the middleware layer does is it includes lots of playbooks where it will convert that simple command into real actions on the proxy system. The middleware layer will then translate the state space from the real proxy system and convert that into the language that the machine learning agent's used to hearing. This project's had some really significant results recently, so these are from like the last probably 2 or 3 months. We're seeing that multi-agent defenders are consistently outperforming single agents. So again, you'll sort of see this convergence in our approach. There's other benefits around multi-agent defenders where they'll offer us resilience. So for example, on a warship, you can imagine battle damage might take out part of the ship. These agents will still be able, the remaining agents will still be able to defend their area of the system. Another interesting quirk of the multi-agent training regime was that these different agents started adopting specialist roles. So you get a specialist isolation agent, and you might get a specialist recovery agent, which is just really, we don't know why that happens yet. It's just really interesting emergent behavior. However, our vanilla approach really struggled. So this is shown in red on the graph on the right-hand side. Our vanilla approach really started to struggle when we put it in harder scenarios where we had uncertainty around the alert delays, false positives and negatives, and probability of action success, up to the point where it could not achieve the level of performance from our hard-coded human defender baseline. How we've overcome that is by using a technique called curriculum learning. So this is like you learn at school, right? You teach the agents on simple tasks, then medium difficulty tasks, and then you keep increasing the difficulty, rather than, you can imagine, chucking a nursery child into a university course. They're never going to get anywhere. So that's shown in blue. So the steps there are where we've increased the complexity of the scenario. Also, we're using action masking, which is quite a simple technique. What you do here is you make the problem easier for the RL agent by masking out just completely ridiculous actions. So you're simplifying the problem, and you're not making it try and learn the basics where, for example, you wouldn't want to isolate a node that's not infected. So you can see on the graph, both the green and blue lines that representing these approaches both started outperforming our hard-coded defender in our difficult scenario. However, when you join these together, the benefits are compounded, and we then start seeing even better performance. So that's where we're up to now. Like I said, in the next few months, we're hoping to reach a major milestone where these agents start making their first actions on a real system and start defending against real attacks, which is a huge achievement for us, and something we never thought we'd be able to achieve 2-3 years ago. We're also starting to try to explore the distributed architectures of these multi-agents. Where do you put them? Do you have one associated with each node on the network? Do you have them managing a subnet, for example? What's the best thing to do here? And there's experimentation underway in that area too. So that was just a run through of a few of our key projects. I'll just touch on some of our overarching key achievements. So before this project, there was quite limited capability, combined AI and cyber capability in the UK defence supply chain. From a small number of companies we now have 30 to 40 active suppliers with expertise in that area, and both teams here will tell you how we're still recruiting in this area to boost the skills. We believe that we've shown a successful proof of concept that RL shows promise in this area. We've also feel that we've extended the ACD and its supporting theory. So a lot of the approaches shown here, there's no publications prior to our work which has shown those approaches being applied to the cyber problem. Like I said, the end-to-end defense of a real cyber attack on a real network is huge. But in terms of the maritime system, once we've done that testing, we believe that's the first reported deployment of ACD to a real military OT system, which you can explain why we're getting so excited about that. In terms of the key results, again, we've shown that RL can outperform rules-based agents, and that difference in performance only increases as you up the difficulty of the problem. I've mentioned the multi-agent advantages over single agent. This also helps with scaling where each agent in a multi-agent solution has a simpler problem to solve than one single godlike agent trying to do everything. I've also mentioned generative AI. So this gives us huge opportunities to scale our training and enhance the robustness of these agents and give them abilities to defend against scenarios that they may not have seen in training. Far higher than if we were to have tried to build the training scenarios manually. We're also seeing, one of the most interesting things is we're starting to see consistent requirements scaling to real. So we've done our big divergence of research. We're now starting to converge on a number of key technologies that are required to enable deployment of these technologies to real systems, and those were shown on the previous graph, but they're also starting to appear in lots of different other projects. So in terms of what's next, we're continuing to increase the maturity of our concepts. We're continuously building in more realistic and challenging applications. We also have future aspirations to build in an integration with the cyber situational awareness area that SJ mentioned earlier. This will allow us to develop more threat-informed defense agents through intelligence such as attribution. So if the agents have an idea of who it is attacking them, this may change their defensive actions. We're also maturing our evaluation approaches. So like I said, we have aspirations for conducting red teaming exercises and user trials. So again, this is reinforcing the confidence that people may have in these solutions in a realistic application. We're also engaging with the user community now. So now we feel like we've got something that's interesting enough to talk about. We're reaching out with the user community, such as the Royal Navy, to start identifying exploitation routes, but also, because of the lead times involved in a defense program, start defining the requirements for those systems to enable future integrations of this type of technology. We're also looking at how do we build trust. So we've looked at full auto solutions. How do we start building trust in that? And we have a research looking into how the human-machine teaming and how we might need to adapt different levels of autonomy to different use cases. So a user on the edge may be far more accepting of fully autonomous cyber defense than a SOC analyst, for example. We're continuing our foundational research into emerging ML approaches. We're also, you might wonder why on earth are we sat here briefing military research? It's quite unusual, right? We appreciate that we can't solve this problem by ourselves, hence ourselves, but also the Castle program here in the US have got a really open knowledge-sharing approach, which I'll touch on in a sec. But our questions here for you, sort of the takeaways here, is how would you defend against these future AI-driven threats where you're just experiencing high volume, high velocity, and high variety of cyber attacks? Do you have places where you can't get a human responder, or if they are there, they might not have the capability or capacity, they might be overworked and might not have the capacity to defend against these attacks? If you introduce these systems, do they bring in new attack surfaces? But also there's other use cases for these types of technologies. We're already identifying opportunities around training human cyber responders, but also automated pen testing for some of our red agent work. Should you start tracking research on ACD and ACO? I'll leave that up to you. But also, we're really interested in the follow-up after this session, like, have you seen areas that you think we've missed and that we should start digging into? I touched on our knowledge sharing here. This is just a small list of the publications that we've released, ourselves and the Turing Institute have released in the past few years. But we're hungry to do more, so we're going to be at the CAMLIS conference in October, I think. We've already got at least one paper accepted to be presented there. So thank you very much for listening. I hope you found this talk really interesting. Like SJ said, we could have sat here and talked for the whole 2 days about this one. Happy to take any questions. We're going to be in the wrap-up room later, straight after this. So really look forward to taking your questions. But thank you for listening.